Hello friends, I am Dr. Kishore Chandra Revatkar, Department of Physics, Dr. Ambedkar College. Today I am talking on a topic, wave optics, in particular interference. Now we can see various phenomena which are associated with the optics or the light. Now if you look at this picture, then almost blue sky is there with a certain cloud, and the water is there. So this is a reflection of light, as we are aware about this. Now the next phenomena, can you guess? There is one image over here. You can see arrow. This arrow above which glass slab is being placed. Then there are two images that will be seen, and this is nothing but the phenomena of refraction of light. In this case, there is a double refraction phenomena. If you know, then there is a extraordinary light, and the one image is a ordinary light image. Now the third phenomena, if you see, the soap bubbles are there and different beautiful colors are appearing over there. This is nothing but the interference of the light, the phenomena of interference. Yes, you are right. Now the next phenomena, again you can see there are certain image will be formed, alternate dark and bright pattern that will be formed in a circular shape, and this is nothing but again the phenomena of interference, and this was discovered by Newton. So therefore these are called as Newton's ring. Now this is ordinary your CD, but there are different color that will be appearing over there. This is a phenomena of diffraction, as we can see. Now again you can see here in this image there is a one bright light, and then alternately bright and dark bands that will be appear, and this is again a phenomena of diffraction of the light. Now you see here from the wing of the aeroplane the light will be reflected, and different color they are appearing, different color that will be. So this is a phenomena of polarization of the light. Now again we come here, you see through the thread that is being connected in a circular loop, and a thin film of soap or any oil that will be formed, and when it will be reflected or irradiated by the light rather than reflected, then we can see the different color bands are there. This is again a phenomena of interference. Yes, and today I'll be talking with you in more detail about the phenomena, different concepts which are related with the. So let us start with this first slides. So what is wave optics? So wave optics is a study concerned with the phenomena that can be adequately explained by the geometric ray optics, and the phenomena which is associated with the wave optics or the wave phenomena, we can say that associated with the light wave in the form of a wave, interference, diffraction, polarization, the other phenomena we have seen like reflection, refraction, transmission, and as such there are different kind of the phenomena, out of which these are very important properties of the light when we consider the light in the form of the wave. So of which today we can see about the more in detail about the interference phenomena. Now then, what is interference? If we consider a light in the form of a wave, they interfere with each other much like a mechanical, as we can see in case of a mechanical wave. All interference associated with the light wave arise when electromagnetic field that constitute the individual wave when they are combining together. Now then, what exactly the interference? Interference means in general you can say that a mixing, or in Marathi we can call it Marathi मध्ये आपण याला म्हणू ढवळाढवळ. Okay, ढवळाढवळ means a mixing together, mixing of the light together. Now when we consider how can we describe the phenomena, so interference phenomena is nothing but superposition of the two waves, in particular the amplitude. As we all know that when we consider wave, it has the one crest and one trough part, so alternate part, or in other way we can say that the positive half cycle and the negative half cycle. Okay, so now when the two identical waves having half cycle out of phase, I will explain what is out of phase and with phase, their amplitude cancel together and they will produce a destructive interference. So, and if the two waves are in phase, their amplitude are constructive. I will explain you what is phase. If you see the term phase, then it is nothing but the position and direction. In what position the wave is there, that means a starting position, initial position, you can say that, from where the wave is starting and in what direction they are going. Okay, so now here you can understand in a much more better way. So we consider two waves. As I told you, this is nothing but a superposition phenomena. So for superposition, we require two waves. So we consider two waves having almost equal amplitude and equal frequency also. Now the maximum displacement, this we consider something to be a mean position. So maximum displacement from the mean position is called as amplitude. And if I start from this point and if I again come to the same, again the wave will start the replicating. Then from this to this we can call it, this distance we can call it as the wavelength. And the number of oscillations in a unit time, how many times the wave is oscillating, is nothing but the frequency. Okay, so now when the two waves overlap with each other or superimpose means exactly coinciding with each other, exactly matching with each other, then in that case the wave amplitude that will be added, and you can see over here the amplitude of this wave is twice the wave of the individual wave. Now the second figure we can see here, the yes, if you start this wave from this point and if we consider this wave start from this point, then we can say that both the waves are starting from the same point, same position, and they are moving in the same direction. We consider that the waves are moving in the right direction. So here also we can consider. Now you see here, this wave is having a positive half, so this is having a crest and this is having a trough. Okay, so these are out of phase and the phase difference is of 180 degree, because this wave is a positive half and this is a negative half. So now when these waves crest and this wave's trough will superimpose on each other, the resultant will be a destructive phenomena, or the amplitude will be almost zero. This can be more understood with the help of this animated picture. You see here, this wave and this wave, now they are in same position. Now they are in a destructive position. When the crest and the trough of this wave will coincide, you can see here the amplitude zero, almost zero. And when the two waves crest and trough coincide, they will produce the maxima. This is what. Now, what are the conditions we require? Now, we have seen the interference means superimposition of the wave. Now, what are the requirement so that we can have the interference phenomena? Very simple. The first requirement that the source should be coherent source. Coherent means the two sources, because we require the two waves, so two sources, they should have same frequency, almost nearly same frequency, and should have same or similar amplitude. Now there are two kind of the coherence that the phenomena are there. One is called as a temporal coherence. Now in a temporal coherence measures the correlation of the phase between the electric field at one location but different time. So location should be same but time should be different. Okay, they will be appearing at a different times. And the spatial coherence, spatial coherence measure the correlation of the phase of the light waves between two different lateral locations. Okay, now how can we produce the coherent source? By old method, you can say that the light from a monochromatic source is allowed to pass through a narrow slit. The simple way, you can take source of light and place in front of it a slit, then the light will come out of it, so that becomes a monochromatic. So monochromatic means, mono means single, chromatic means color, that means a single wavelength light. So light from a single slit is allowed to fall on a screen containing two narrow slits. So from single slit we can again divide the light into two parts by using the two narrow slit, placing in front of the single narrow slit, as is been done by the Young's experiment. The first slit is needed to ensure the light comes from a tiny region of the source which is coherent. Tiny region means a small point, so that the wavelength the frequency, the amplitude of the light should come down. Now there is another way of producing a new method, we can say that. And in the new method, currently a laser light that has been used, because we know that the laser light is a coherent source, because it is highly convergent. The light wave is convergent and all the waves are in phase. So now this is another important phenomena before we actually proceed for interference. Now what is the phase change due to reflection? Now you can see here there is a solid medium one here, and this is a, or in other word you can say that we have a denser medium and we have a rarer medium. Now when we allow the light to incident on the denser medium, that means refractive index, you can see N2 is greater than N1, so this is a rarer medium, this is a denser medium. So when the light will be reflected, electromagnetic wave undergoes a phase change of 180 degree upon reflection from a denser medium, that means a higher index of refraction analogous to a reflecting string. I will explain what is that. So therefore when the light is reflected from the denser medium and coming from a rarer medium, then there is a phase change of 180 degree. This is being shown by this. So this is the incident light, you can say this is a crest. When it will fall on the material, solid wall or any material, then this is the incident wave, and you can see here after reflection there is a phase change, so crest becomes a trough. This is been explained with the help of this animated picture. So the string will be moving and it will be reflected and again it will be changing. So the crest will be converted, yeah, you can see crest will be converted into trough. This is how. So this is analogous with the string. Very simple experiment you can perform at home. You can tie one end of the string to a solid wall, and then you can give the jerk to the string like as will be shown in this figure. Then you can see actually what will be happening. So now the phase changes due to reflection. Now in this case what will be happening, that there are two mediums we have considered, N1 and N2 medium. So N1 is denser and N2 is rarer medium. Now the light is traveling from the same medium and it will be reflected from the rarer medium. So this is from denser to rarer medium. This interface is a rarer medium. Then there is no phase change when the wave is reflected from a boundary leading to a rarer medium, that is a lower refractive index. This has been clear over here. So this is the incident rope tied over here loosely, that is a free support. When it will goes here, so it will be coming back, the crest will be coming back like a crest. You can see here. So this is the incident ray, okay, incident ray, and this is a rarer medium here we consider. So now after reflected, you can see again the crest the same way, there will be no change in the phase. So analogous to a pulse in a string reflected from a free support. This is being shown over here. So this is a free support incident light, and again you can see here the same wave will be reflected back. Now let us come to the interference phenomena. Now how the interference phenomena that will be result. The light from the two slits forms a visible pattern on the screen. So we can take two slits and we allow the light to move forward through the two slits. Then the pattern that will appear on the screen will be alternate dark and bright bands. So there will be dark and there will be bright parallel. Of course, they are parallel to each other and they are called as a fringes. The bright band appears over here is due to the constructive interference, because we know what is constructive interference. When the crest will superimpose crest and trough will superimpose trough. And in case of a dark, the crest and the trough will superimpose on one another. So therefore that is a destructive interference. Now here we can see this exactly, it will be clear more from the Young's double slit experiment. Thomas Young has first demonstrated interference in light waves from the two sources. Now what he has done, he has taken a source of light S0. So that will be incident on the screen. This is the screen, and then there is another obstacle that is being placed where there will be two small pinholes are there. So now the light wave emerging from the slit arrive at the second screen. From here it will appear over here, and it will contain a two narrow parallel slit S1 and S2 over here. Now this narrow slit S1 and S2, they will act as a source of the light. So now the waves emerging from the slit originate from the same wavefront and therefore are always in phase. So because from same wavefront, you can see this is one wavefront, this is another wavefront. We can say that this is a crest, this is a trough. So crest is appearing over here, crest is appearing. So when the light will come out, so crest will come out here and crest will come out here. After that crest, there will be a trough like that. So now there are two sources. One is S1 and another one is S2. So now when I consider the thick line as a crest and the white portion, no line, I consider as a trough. So now you can see here very carefully, when the crest will coincide with the crest of the another wave, then you can see there is a bright point will be there, and that leads to a maxima. And straight also you can see here a maxima will be there. So alternately anywhere you can see this light and the source due to this S2 and S1, then they will shows a dark, that is a maximum. And when the white portion will coincide with the white portion, that is a trough, and the crest due to one, when they will you see here, any point, this is a crest over here and the white portion will trough due to one wave, so they will produce a minima. So that can be seen over here also. So alternately you can see bright dark, bright dark, bright dark. So these are the fringes that will appear. This is what the Young's has demonstrated. Again, it will be more clear for you from these pictures. So we consider Young's experiment. We can consider a sunlight, a parallel beam of light we can obtain. There is a one single narrow slit, then the light will deviate like this. Okay, then there are two slits, 1 and 2. This I call it as a right slit, this I call it as a left slit. When both the slits are open, you can see in the middle portion, as we have seen over here at the center, see this is a maxima that will appear. So maxima will be appear, followed by the darkness, and alternate you can see here. So now again we will see more clearly. So this is a source of light. Now when I keep the right slit open, this is what we can observe the light. If I open the left slit alone, then this light will appear. And if I keep, this is the first slit, S0, S1 and S2, when both the slits will appear, you can see at the center there is a maxima that will appear, followed by the dark, then bright, then dark, then bright, and alternate dark and bright fringes lines appear. So these are called as the fringes. And this will be again more clear for you. So these are the two double slits, and the source of parallel beam of light will be coming alternate. So this blue line I consider as a crest, and the other I consider as a trough. So when that will coming out, you can see alternately the interference phenomena or pattern that will be appearing. So this is the top view we can see from the top. So see crest and the trough also. Now this Stokes relation is very important in order to understand the interference in the thin film. Now let us start with a ray of the light A having an amplitude A. So that will be shown by a blue light. So when it will fall at certain point, so there are two mediums. One is a rarer medium, air medium, and the lower is a glass medium, that is a denser medium. So now when the light will come over here at this point, so this is a normal position, you can say that. Then from here, one part of the light will be reflected. So that magnitude of the reflected light, I consider A is the magnitude of incident light. So reflected light is having a magnitude AR. Part of light will be transmitted. So here it will be divided into two parts, reflected and transmitted. So that will be AT. So shown by the blue line. Now what I can do, I can reverse this. So that from here I start, from here, okay, from here we can start AR. So now we consider If I consider the AR will be the amplitude of the incident light, then what will happen? It will go in this direction. So AR is already there, amplitude, and again because of reflected, so ARR, that is AR square. Okay, and then here it will be transmitted back. Okay, here it will be transmitted back. So therefore AR into T. Okay, AR into T. Now I reverse this light. Okay, transmitted light. Now when I reverse this light, so having amplitude 80, that is already been there. So when it will go, so it will be reflected in the same medium. Okay, so now when it will be reflected from a denser to rarer medium, there will be no change in phase. But here, as we have seen, when the light coming from the rare medium and reflected in the from the denser medium, there is a change in the phase that will taking place, that will come appear in the next slide also. So now let us come to this. So transmitted light will be reversed. So what will happen? It will be reflected in this direction. So AT into R dash, because of the reflection. R dash from the glass medium I consider, R from the rare medium, air medium, and here it will be transmitted light. So when we add this light, here, then from this equation I can write down A equals to, because initially that was A, so A equal to AR square plus AT dash. So AA cancel, so R square plus TT dash, this TT dash is equal to 1, because AA will cancel, and here initially there was no light, so therefore 0 is equal to ATR dash and ART. So AT will cancel out, so R is equal to R dash. So that means, what does it means? That when the light reflected coming from the rare medium and reflected from the denser medium, the R dash for glass medium we have considered. So there is a phase change of 180 degree that will takes place. Okay. Now the same phenomena we can apply here in case of a multiple beam interference. Okay. Now A I know, we also know A is the incident light, then this is a normal, then the angle made by the incident light with the normal is called as I, and then this angle we can say that the R reflected light. Now when it comes over here, it will goes AR. Now part of it will go AT. Then from here it will come out the transmitted light. So this is a transmitted light. Then from this light, this will again go back. So this is a refracted light. Again there are multiple refraction taking place, and as we move away from the main light, the amplitude of the light, that means intensity, will be goes on reducing. Similar, this refracted light will be coming out. So AT R dash and T dash, because it will be coming from the thin film. So now this thin film we consider having a thickness D and refractive index mu we consider. Okay. So now we'll proceed further. So now interference pattern we can see. We have seen that when the two waves coinciding, crest and trough, they will produce a maxima. So same we can say that constructive interference occur at the center point. So we have seen that at the center point there will be a bright. So at the center point it will be bright because the two waves travel the same distance, because they are coming from the same distance. They, even though they are inclined at this particular point, but the path difference will be 0. So therefore they appear with the same phase, and there is a constructive interference, or at the center we have the bright. Now in this case, constructive maxima also, not necessary that every time at the central line, at the equal center point we have seen that there will be a maxima, then minima, maxima, minima, maxima, dark, bright, dark on the upper side, on the lower side also. But at certain point, if the point is appear to be bright, that means that the interference is a constructive interference. So the upper wave travels one wavelength further, you can see, because this has to travel little bit more path. But when they are these two waves, even if after traveling more path, if it travels in a integral multiple of its wavelength lambda, I will come to that equation, but remember this, in a multiple of wavelength lambda, then the phase will be same and the fringe appears to be bright. But in case if the trough at the bottom of the wave overlap with the crest of the upper wave, yes, if the path is not equal to integral multiple of wavelength lambda. So crest of one wave will coincide, crest of this S2 wave will coincide with the trough of this, then that particular point appears to be dark and a dark fringe occurs over here. Now we can see the equation, the same equation we can see. So S1 and S2, the two waves are coming out. So from S1 we consider R1 is the wave, and from S2 it is R2 wave. So now if you consider the distance from here, point P from S1 and S2, then the distance between S1 and S2 we consider will be equal to D. This is the source of light. Now the light will going out in this direction. At the point O we get a maxima, but this particular point, whether it is a maximum or a minimum, that will be depending upon the path between, because if you measure the distance from S1 and this particular point which is shown by the dotted line cut down, then by using a tangent triangle, this delta is the additional path this wave coming from the S2 has to travel. So therefore delta is equal to R2 minus R1, because R2 is greater than, and if from the triangle tan of triangle law, if that is equal to D sine theta, this assumes to be a parallel path. So from S1 and from this particular point, this will be a parallel path. So note that exactly if the paths are not parallel, not exactly, but a very good approximation, since L is much greater than D. So this distance of the screen is much larger than the distance between the S1 and S2. So now we can see over here. So as I told you, when we have the constructive interference, when the delta means this path difference between the two waves coming from S1 and S2 is equal to n lambda, that is the integral multiple of wavelength lambda. N is equal to 0, plus minus 1, plus minus 2. So n is equal to 0, we get the zeroth order, that is a maxima, and when n is equal to plus 1, plus 2, plus 3 is called a first. For plus 1 it is a first order maxima, plus on one side and minus on the other side of the central maxima. Then in that case the interference is a constructive interference, and if this delta, that is a D sine theta, will be equal to n plus 1 by 2, half integral multiple of wavelength lambda. So if I put down n is equal to 0, so it will be lambda by 2. So path difference between the two waves will be lambda by 2. Okay. Or if I put down n is equal to 1, it will be 1 plus 1 by 2, that will be 1 plus 1 by 2, how much it comes? 1 plus half, 1 and half. Okay. So 2 plus 1, 3 by 2, you can say that 1 and half means 3 by 2 lambda, 5 by 2, if I put down n is equal to 5 by 2, 7 by 2. So half integral multiple of wavelength lambda, then the interference will be a destructive interference. Now interference in the thin film. This is a thin film, oil film, where the different colors will be appearing because of the reflection of the light. So interference effects are commonly observed in thin film, as I told you. Soap bubble is a best example, or if you spill oil on a water surface, then this interference is due to the interaction of the waves reflected from both the surfaces of the film, both the surfaces of means upper surface and the lower surface. Okay, so this is a common example that we can see, common view we can see in the rainy season. If we move across the road and if the oil is spilled out from the vehicles, and if there is a water on the road, then the different colors, when the sunlight is there, different colors that will appear. So this is what is the best example, because the oil will form a thin film. So now this actually we can see, what is this? This I consider soap film. So it is having certain refractive index. So this blue color is the incident light, this green is a reflected light, then this pink color we can say that is a refracted light, because that will be coming out from the inside of the film, and this is a refracted light, you can see here, refracted, then it will go here, and this is a transmitted light. This is a actually not a refracted light, this is a transmitted light. Okay, so now this we can see, actually suppose I consider this like this is one wave. So ray 1 travels into the thin film and back it travels to this 2t. 2t means this I consider as the thickness of the film. Small t is the thickness of the thin film. Then this is a trough, this is a crest, trough, crest, trough, crest, trough. So then it will go like that. That will enter inside, and from here one part of the light will be reflected, another will go inside the transmitted, then this is actually transmitted light. Then from this particular point again it will be refracted, this refracted light will be coming out. So we consider these two parallel rays, this green and this pink rays. Okay, so now if they will go like that, you can see here the crest, 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 then in that case we should expect that the reflection are in phase. But if the crest is coinciding with the trough, then in that case it will be a destructive interference. So the path difference between the two rays when they come out of the film, it should be 2t. So that will be more clear. So now ray 1 undergoes a phase of 180 degree, as I told earlier, because this is been light is traveling from the rare medium and it will be reflected from the denser medium. So this ray 1 has 180 degree of phase change, while this light will be coming from the denser medium and coming out, so it will be having no phase change. This is very important. So now thin film interference, as we have seen, the ray 1 and ray 2, when they will be seen through the eyes like this, if we see this through the eyes, then we can have the constructive interference 2t, 2n times t. 2t is the distance, because once and twice it has to go. Okay, and then for constructive interference, m plus m will go to 1 2 3 4, you can say that. So these two will come out, so the in this direction, so that we get the constructive, the equation for the reflected light. Keep in mind, this is the equation for the reflected light. So 2 times nt will be equal to m plus 1 by 2 lambda. Then these two will come out over in this direction. And for destructive interference, twice nt is equal to m lambda, where m is equal to 0 1 2 3. So these are the best example as we come in our daily life example. These are the soap film, and when the light will fall on it, sunlight, they will there appears to be a different colors. Now Newton's rings are, as I shown in the very first or second slide about the Newton's ring. I told you that Newton has discovered these rings and he has given the satisfactory explanation. But earlier these rings was observed by Robert Hooke, but he could not explain it, and later on Newton has given the explanation. What he has done, Newton's ring experiment is simple experiment. We can take a plain glass plate over which a plano-convex lens we can place, and then there is a glass plate we can keep it over here, which is inclined at a degree of 45 degrees, so that whatever ray that will fall, they will be reflected in that direction, in the direct exactly normal to the plano-convex lens. There is a source and then this is a convex lens, so that the convergent light will be made parallel. Then from here the one ray of light will be reflected and again it will be reflected back. So this light will be incident light and reflected light, you can see over here. So this light will fall from here and then the light will be reflected from this surface, and then again it will there is a gap. So this film is a vase-shaped film, and from lower surface again the light. So these two lights, when they are observed, so they will shows alternate bright and dark rings. So why we are getting a circular ring? Because we are considering the plano-convex lens. This is a circular shape, so that there is a vase-shaped film that will be formed in a form of the circle. So now these rings will appear something like that. The center will be bright and sometimes the center will be dark. If the center is bright, then in that case we can say that it will be due to a reflected light, and if the center is dark, then it will be because of the transmitted light. So when we study the Newton's ring, we measure the diameter of the various ring or radius of the Newton's ring from the center. And if we plot a graph, so these are the number of rings, number 1, 2, 1, then 2, then 3 and 4 and 5 and 6, and likewise number of rings and versus the radius, then you can see that as the number will be increasing. As we move away from the radius, we see that the radius, we can see there is a diameter that will be increasing. Diameter of the ring will be increasing. And if we plot a graph between the radius and different color, blue color, green color and yellow color, then you can see because the blue color has smaller radius than yellow color and the green color, because the wavelength of the blue color is smaller. So that will be very clear from this equation. Rn square, radius of the Newton's rings, will be equal to Nr, where capital R is the radius of curvature of the plano-convex lens and lambda is the wavelength of. So Rn square is directly proportional to R. Similarly, we can calculate the wavelength of the monochromatic light by using the Newton's ring. This is a simple formula, that that dn square is the diameter of nth ring minus dn plus p square, then divided by 4pr. Okay, so where r is the radius of curvature of the lens, p is the distance difference. So actually we require dn plus p square minus dn square. It should be the other way. Okay, anyway, so this is how the Newton's ring that will appear on the screen. You can see this is a bright spot because of the reflected light, and followed by the dark ring, then bright ring, then dark ring, then bright ring and dark ring, and so on and so forth. As you move away from the radius, the number of rings will appear and the diameter that will be increasing. Okay, so this Newton's ring will appear something like this. Okay, so thank you very much. Here I end my presentation on the interference. Hope you like this presentation. If you like it, then please share with your friends and give a